call is now being recorded.
Tá gravando.
Okay, welcome everyone. It's a pleasure to introduce Rodrigo Gondim from Federal University of Pernambuco, Universidade Federal Rural de Pernambuco. It's a pleasure to introduce him. He will talk about wiring problems and the Lefschetz properties. Please, Rodrigo.
Hi, everyone. It's a pleasure to me to be part of this BRAG seminar. I would like to thank the organizers for the invitation, especially Mauricio and Carolina. I'm going to talk about wiring problems and Lefschetz properties. It's joint work with Thiago Dias that we just finished 1 month ago. The preprint is in archive. So let me start recalling what is the wiring problem in number theory. In number theory, the wiring problem is the search for a given exponent k for the minimum s such that every natural number can be decomposed as a sum of s perfect k powers. The first result in this direction was conjectured by Fermat and proved by Lagrange, is that every natural is the sum of 4 squares. We also know that any natural is the sum of 9 cubes, 19 fourth powers, 37 fifth powers, 73 sixth powers, and that's it. The problem is open in general, but the classical result of Hilbert is that the wiring problem is well posed in the sense that for every k, for every exponent k, there is a finite s such that every natural number can be decomposed as a sum of s perfect k powers. In analogy with the classical wiring problem, there is an algebraic version that asks what's the minimum s such that any homogeneous form of degree d can be decomposed as a sum of s perfect these powers of linear forms. We will work over C for simplicity. This version was solved by Alexander and Rishovich, studying the higher secant defect of the Veronese varieties. The idea is very simple. We can consider the image of the Veronese as the polynomials that are actually a power of a linear form, and the polynomials that are a sum of 2 linear forms are belongs to the second secant of the Veronese, and so on. Polynomials which are the sum of at most k powers of linear forms belongs to the the kth secant variety of the Veronese, and the expected dimension of the Veronese is given by Terracini lemma. It's just Terracini. And that's the formula, and the condition for the secant of order k of the Veronese to be the ambient space. The ambient space is P n plus d choose d minus 1. So is this condition, and make the calculations. We get this bound, and the minimum k is this one if the Veronese has no secant defect, and there are only a few numbers of exceptions, and these was studied by Alexander and Hitchowitz. So this version was solved, and we are interested in variants of the Warring problem, not a global one, but for a specific f. And we define 3 different notions of rank of a homogeneous form of degree d in n plus 1 variables. The Warring rank of f is the minimum s, such that f can be decomposed as a sum of s these powers of linear forms. So the Warring rank of the generic polynomial is just the calculation we did for the generic polynomial. The border rank of f is of geometric nature. It's the minimum s such that the class of f belongs to the s-secant variety of the Veronese image, of the Veronese variety. It's equivalent to say that there is a one-parameter family of forms of Warring rank S whose flat limit is f. The border rank of a generic polynomial is equal to the Warring rank, but in general, the border rank, the Warring rank is an upper bound for the border rank. And there is the schematic rank, which is also called the cactus rank. The cactus rank of f is the minimum s such that there is a finite scheme of length k in the Veronese such that f belongs to the linear span of the scheme. We know that the border rank is bounded by the Warring rank. Also, the cactus rank is bounded by the Warring rank. But the cactus rank and the border rank are incomparable in general. The most exotic behavior is when the cactus rank of f is greater than the border rank. In this case, we say that the form is a wild form. The terminology wild form was introduced by Budzinski, and they constructed the first example of wild form. These are very special forms in the sense of the ranks that we just mentioned. And it's very interesting, as it was observed by Giorgio Ottaviani, that told Francesco, that told me that the example is equivalent to the Perazzo example of a form with vanishing Hessian. There is only one cubic hypersurface in P4 up to projective transformation with vanishing Hessian. This one is a projective variation of the original Perazzo form that he called un esempio semplicissimo. It's very interesting because in this case the Warring rank is 9, while the border rank is 5. In fact, it's it's easy to find an explicit decomposition of one parameter family whose limit is f with 5 summands. In fact, the border rank is 5. On the other hand, the cactus rank for this example is 6. It's not so easy to prove that it's actually 6, but it's easy to see that it's at most 6, because f is the sum of 3 double points in the Veronese. So it's a finite scheme of length 6. So the cactus rank is at most 6. In fact, the cactus rank is 6. And to conclude that the cactus rank is actually 6, the authors, Budzinski, studied the saturation of the annihilator of F. This idea of studying the saturation of the annihilator of F to control the cactus rank and use some geometric properties of F to bound the border rank was generalized by Huang, Michalak, and Ventura. In the same time, we are, Thiago Diaz and I are studying this problem, and they put a preprint proving that if F is a concise form, concise means it's not a cone, the hypersurface is not a cone. There is no linear relation among the partial derivatives. With minimal border rank is the number of variables. I'm not explaining this, but that's the point. So in this case, if the Hessian is vanishing, then F is valid. So it's not a coincidence that the example semplicissimo of Umberto Perazzo was the first one to appear. It's also the first one of a concise form with vanishing Hessian. And meanwhile, we are studying the same problem, but using a different approach. And let me explain how they are connected and why the Lefschetz properties appeared in this context. It was Watanabe, Maeno and Watanabe, that showed that the Lefschetz properties for Artinian-Gorenstein algebras can be controlled by the Hessians. Let me recall the definitions. What we call Lefschetz properties are abstractions introduced by Stanley and also by Watanabe, inspired by the hard Lefschetz theorem on the cohomology of smooth projective complex varieties. For any Artinian, standard graded Artinian K algebra, we say that the algebra has the strong Lefschetz property if there is a linear form such that all the multiplication by powers of L from degree K to degree K plus J all has maximal rank, and you say that A has the weak Lefschetz property if the multiplications by L have maximal rank from a K to a K plus 1 for any K. We are particularly interested in AG algebras, Artinian-Gorenstein algebras, one can characterize these algebras as Artinian, standard graded Artinian K algebras satisfying Poincare duality. So we are actually in the context of homology algebra. And a very important result of Macaulay-Matlis duality says that these algebras can be presented by a quotient of a polynomial ring of differential operators module the annihilator of a single form f. So we are considering R as the normal ring of polynomials in the variables x0 to xn with a small variable x, and Q with capital X are differential operators that act in R, xi, capital Xi acting on small xj is the delta of Kronecker. So it's just a differentiation. And given a polynomial f in the ring of polynomials, f is here, the annihilator of f is the set of differential operators in the ring of differential operators that annihilate f. It's an ideal of Q, and it's easy to prove that it's Artinian ideal. It's a little tricky to prove that it's Gorenstein, and the converse is also true. Any Gorenstein, any AG algebra can be presented in this way. It's very useful. Oops. Aha. Oops. So the generalization of the original idea using normal Hessian is to consider mixed Hessians. Mixed Hessians were introduced by Giuseppe Zappalà and myself some years ago, generalizing the ideas of Manuel Watanabe to understand the Lefschetz property. It's very simple. We consider Q the ring of differential operators, model F, and BK is a k-linear basis of AK. So differential operators of degree K that do not annihilate F, and also BL, k-linear base of AL, and the mixed Hessian of order KL of F with respect with this base, but it's not important the basis. We are just interested in the rank of the Hessian. Is the matrix alpha I bj of F. We define hash K with capital H, the hash KK, and with small h, hash K is the Hessian determinant. And it's easy to see that hash F is hash 1F is a generalization of the Hessian. And there is this technical result that's very important. The first part was proven by Maeno Watanabe for higher order case determinant, but we generalize in this setting. The multiplication from AK to AL, the rank of this multiplication is the rank of the Hessian. In fact, the matrix of the multiplication is the matrix of the hash evaluated in the coefficients of the linear form L. Here we are considering L, A0, X0, N, AN, XN. Sorry, it's N here. N. Sorry. So, to understand the rank of the multiplication in the algebra, it's just to understand the rank of the Hessian. Let's move. So it's I don't have time to explain in details these osculating space idea, but it is the principal, the main ingredient to get this upper bound for the border rank of a class, a special class of B-graded forms. If you consider B-graded forms with degree k in the variables x and degree d minus k in the variables u and v, we get this bound. The idea is quite simple. We are looking for wild forms. Wild forms is this condition: cactus rank greater than the border rank. The idea is to find an intermediate bound such that the border rank of f is less than or equal to 10 which is less than the cactus rank of f. So we are looking for an upper bound for the border rank of special forms, of course, that are at the same time a lower bound for the cactus rank. So to control, to get an upper bound for the border rank, we use these osculating spaces. I do not have time enough to explain. And to get a lower bound for the cactus rank, we have to study the saturation of the annihilator of F. That's the point. Let me introduce some notation. A form F in RD is called K concise if the annihilator is 0 up to degree K. It's equivalent to say that the Hilbert function of the algebra A is maximum up to degree K. K concise. And you got this lemma that a K concise form, the algebra associated to a K concise form, if the Hessian of the form is degenerated, I'm talking about the Hessian, the matrix, then there is an element in the saturation of the annihilator in degree K. Recall that the ideal is 0 in degree K, but there is someone in the saturation in degree K. the idea is simple. Thinking the Hessian as a matrix in the, you can think in the ring R. The degeneration of the Hessian is equivalent to the existence of a alpha in the intersection of the kernel of the multiplication for L to the D minus S minus K for every L. In particular, if you take the variables, the L as the variables, we got that xi to D minus K minus S times alpha belongs to the ideal in degree D minus S. So alpha belongs to the saturation of I in degree K. It's very simple. So as I said, the existence of a form in the saturation was the first idea of Buczynski, generalized by Wang, Michalak, and Ventura, and here generalized by us to get a lower bound for the cactus rank. And then we got a generalization of the main result of Wang, Michalak, and Ventura, that a K-concise homogeneous form, if the Hessian is 0, then the cactus rank is bigger than the binomial of n plus k choose k. In particular, if the border rank is less than or equal to this number, the f is wild. So the main result of Wang, Michalak, Ventura is a corollary. If you take one concise forms, we just have to look to the binomial of n plus 1 choose 1, which is n plus 1. Minimal border rank is just border rank equals n plus 1. Since f is one concise and is 0, our result implies that the cactus rank is greater than n plus 1, so f is what? But we also get some examples of forms, wild forms, whose border rank is not minimal. On the contrary, the border rank is huge. For instance, these, if you take these f, which just Perazzo type, but if you take the G, G is this guy, and F is G to the 16th power. We know that F has vanishing Hessian because G has vanishing Hessian, and any power of a form with vanishing Hessian has vanishing Hessian. But it's very special, and we get a bound for the border rank using the osculating spaces, and a border for the cactus rank using the previous theorem. And the minimal border rank in this case is 5, but we are in 4,000. There are wild forms with very huge border rank and cactus rank. That's the point. Moreover, we also get examples and families are formed with non-vanishing Hessian, but with degenerated mixed Hessians. And we get another saturation type lemma. If there is saturation in some degree, the cactus rank is bigger than something. Uh-oh. If you get saturation degree L for some L less than or equal to K, the cactus rank is bigger than some binomial, which is the Hilbert function. There is a small difference in the ideal. We are just taking the graded piece up to degree D minus K. It's a technical reason. And we got our main theorem that generalizes the other ones. If except for the unimodal hypothesis. Okay, let F be a K-concise homogeneous form of degree D, and L and S integers L and K between L and S. Suppose that the Hilbert function of A, the associated algebra, is unimodal, so it has no valleys. It's symmetric by Poincare duality, but has no valleys. If the Hessian, mixed Hessian of order LS is degenerated, or equivalently, the multiplication D minus S minus L to the power of DL to the power D minus S minus L from AL to AD minus S is not injective, then the cactus rank is bigger than the Hilbert function, which is this binomial n plus k choose k. In particular, if the border rank is less than or equal to ak, then F's out. And actually, the proof is just to use the previous lemma. We consider two algebras. The algebra A is Gorenstein. It is Q modulo the annihilator of F. In the algebra B is not Gorenstein, but it is Q modulo J. J is the ideal generated by the graded pieces of I up to degree D minus K. And we get some inequalities among the Hilbert functions that can be summarized in these. AL is equal to BL because L is less than K, and up to degree K there is nothing. It's less than or equal to AK by unimodality. It's equal to BK because there is nothing, because I is K concise, so the Hilbert function is maximal up to degree K. It's less than or equal to AS by unimodality. AS is equal to BS by another assumption. Oops. Is this one. And again, Poincare duality. So there is a gamma in the saturation of I in degree L, and hence we get something in the saturation of J in degree L, and use the previous lemma, we got that the cactus rank is greater than n plus k, choose k. So using so we not necessarily have to use forms with vanishing hashing. The first example of a form with second hash, vanishing second hashing, whose hashing, the classical hashing is not vanishing, was given by Ikeda. And it's this one. It's too concise, and the second hashing is 0. And you studying the osculating spaces. We got this upper bound for the border rank of this piece, and the border rank of monomial, it's easy to control, is a classical result. So the border rank of f is at most 10. But since the second Hessian is vanishing, the cactus rank is bigger than 10. So f is valid. And using this same argument, we get an infinite family of forms with non-vanishing Hessian. The first Hessian is non-vanishing, but the Hessian of a higher order is vanishing, and controlling the border rank by studying the osculating spaces, we get one bound, and if k is big enough, then f is valid. That's it. Thank you.
Okay, let's thank Rodrigo. Any question or comments?
Yeah, I have. Hi, Rodrigo. Hi, guys.
Hi.
Can I start, Mauricio?
Yeah, please, go ahead.
So you said that in general, border rank and cactus rank, you cannot compare them.
Yes.
Right? But even for a general form, it's not expected that the border rank should be greater or equal than the cactus rank.
For a generic,
yes,
f, using the argument of the secant varieties of the Veronese, one expects that these concepts coincide. Because for a generic f, it is not in the border of the secant, the k secant of the Veronese. It's not in the border. It is actually a point in the interior of the linear span of k points in the Veronese.
Okay. Okay. So, and by the duality, you have this k points to be the dual of the guy, which will be the cactus rank. For the generic form.
For a generic form, this argument shows that the border rank coincides with the Waring rank. And since these points have multiplicity 1, there is just a small argument to show that also the cactus rank coincides in this case.
Okay. Okay. And is there any hope for the classification of the forms which all the things? No, because they are generals. I will note it down here to ask you if there is a hope to classify forms with border rank equals to Waring rank, and even forms with cactus rank equals to Waring rank.
No, it's the generic case.
Yeah.
There is a hope for a classification, at least in small degree and a small number of variables of wild forms,
Ah.
because these are the special ones.
Yeah.
The good ones, the generic ones,
Yes.
are an open Zariski site.
I see. I see.
So how the forms such that the inequality is reversed called? So these are the wild and the others are what?
That I couldn't find that name in the literature, but I see some examples, but I
So
there is no
and
name.
they are less interesting than the wild ones? Why?
Yes, because there are some families very well known. These wild forms are very recent, have been very recently discovered, so they are more exotic.
So, are there another questions, comments?
Are there other notions of rank that are interesting in this context?
Yes, for instance, to be fair, my definition of wild form is not the original one. It's a slight modification. And the original definition used the smoothable rank. This is a very important, but it's it's a mess. That it's not easy to compute the smoothable rank. But in this case, the smoothable rank coincides with the cactus rank. So the point is that the saturation of the apolar of F is related with the cactus rank, not with the smoothable rank, because the smoothable rank has a deformation. It's an important concept also.
Thank you.
Okay, another question. So let's thank again Rodrigo for this nice talk.
Beto!